atomic mass is the third part on the periodic table. And in that video earlier, they called it atomic weight, but it's really a mass because weight has gravity, blah, blah, blah. Anyway, atomic mass is the last big thing we need to talk about what that means. And it has to do with the isotopes. So as we talked about earlier, boron can come in boron 10 and boron 11. And in that mass spectrometry slide I just showed you, it's roughly 80% boron 11 and roughly 20% boron 10, all right? At least on the Earth, as far as we know. One day maybe there will be more implications of this. So the atomic mass you can think of is the average mass of all the boron ever seen, all right? So what you can do, and this stems from math, is you can find the average mass based on how abundant they are. This little nomenclature is a little bit weird, but what it means is, first of all, you add up all of that's the summation sign in math, and you want to add up all of the abundances times the mass of that value. So for example, in our system, we have two values. We have two values of I, and one of them is for the boron 10, and one of them is for boron 11. And the abundance is usually just the decimal version of the percentage. So 20% would be 0.20, and 80% would be 0.80. So if you wanted to find the average mass of boron, you could do this quick little math, and it comes out to be 10.8 AMU. And this 10.8 number is the atomic mass. It's the third thing that's on the periodic table. So a good periodic table will have the atomic number, so you know which number it is. It'll have the symbol for the element. And the third thing now is the atomic mass. And they all stem from the averages of the abundances and how many isotopes there are. This handout right here, the isotope abundance handout, will talk a lot more about this. And it's in your companion and it's online. If you can't find it, let me know. Check that out if you need some more details about how this works out. Isotopes give some crazy values sometimes, but it's nothing you can't do. So lithium has two main isotopes as an example. 7.5% of the time you'll have a lithium 6, and 92.5% of the time you'll have lithium 7. So if you wanted to know the atomic mass of lithium, you technically don't need that information at all. You just look it up on the periodic table, and it's 6.941. So the atomic mass comes from the periodic table. I'm trying to confuse you here with numbers and blah, blah, blah. You don't really need it. You just look at the periodic table to get it. Now, how they got that 6.941 was they took the 6 of lithium, multiplied it by 0.075. They divided 7.5 by 100, and they added that to 7 times 0.925. And to better sig figs, you can get 6.941, but you get the idea. Now, for silicon, you can do the same thing. And so silicon has all these different isotopes. But again, the number that's on the periodic table for silicon, you can look it up. It's about 28 or so. They got that by taking the atomic number times the percentage in decimal, and they added it to the other two systems to get it right there, and you're good to go. Silicon on the periodic table is 28.086. That's just a number you look up, but that's where they're getting these numbers. All right, it's all based on it. Now, notice that in the first one, the average mass was about 6.9, all right? And that's much closer to 7. That's because most of the mass is lithium 7. So the average will always be closer to the higher abundance isotope. And in silicon, it's the same thing, that 28.086 or whatever the number was. Most of the silicon is silicon 28. More than 90% of the time, that's what you've got. So that's why the average mass is closer to silicon, stuff like that. Here's an example of a problem you might see. Here's an element. It doesn't exactly say what it is, but element 72 is 54.5% of the time abundant, and 73, 15.6, and element 70, the number 74 there, 29.9. What's a reasonable atomic mass? So the best way to do this would be to take 72, the atomic number, and multiply it by 0.545. Like you take those percentages 1000 divided by 100. And you'd add that to 73 times 0.156 and add that to 74 times 0.299. And if you get all that, you'll get one of the answers down there. Now, if you look at those numbers, there's a lot more 72 than there are 73 or 74. So it's going to be something around 72, but only half of it, I would guess off the top of my head, it's probably answer B. But when you do the math, that's the best way to do it. Definitely going to be answer B. Here's another problem. We had nitrogen has two main isotopes, nitrogen 14 and nitrogen 15. Notice the abundance. The one is almost 100, but not quite 100%. The other one is almost, but not quite 0. It's barely 0.5%. And it says calculate the average atomic mass. So again, what you do is take that AMU mass and multiply it by the percentage divided by 100. So 99.6299 becomes 0.996299, and 0.3701 becomes 0.003701. So we do that over, it gets some weird math, but it comes out to be 14.0068 AMUs. That would be the number on the periodic table. That's how they calculate these things. Now, here's a question you might run into. Gallium has two main isotopes, gallium-69 and gallium-71, and you can see the masses there. The average atomic mass, i.e. the value from the periodic table for gallium, 69.723. You can use this information to calculate the percent abundance of each isotope, and this works as long as you only have two isotopes. So what we're going to do to solve this is we're going to set it up similar to what we did in the last problem. We're going to have the average, which is 69.723, equals the mass of the first one, 68 whatever, times its percentage. So X here is going to be the percentage of the 69. And we're going to add it to the mass of the second one, that 70.9 number, times the abundance of the other one, which we'll call Y. So you can see right now we have two unknowns, X and Y. And those are the two percentages of the gallium-61 and gallium-71. And those are tough to solve. However, the two abundances together have to equal 100%. Or if you're talking about them not in decimal version, 1, which is 100% in decimal, 1 equals X plus Y. So what you can do then is have one of them, we'll say Y, equals 1 minus X. If you subtract X from both sides on that last one, you get Y equals 1 minus X, and you're good to go. So what we're going to do in a little bit is we're going to substitute this part right here, the 1 minus X, we're going to substitute it up here. Then we're going to have one equation with one unknown X, and you can solve for X, and at the very end go back and go 1 minus X to solve for Y. Now X and Y are going to be decimal percentages, which you can multiply by 100 later if you'd like to. So here's the math involved. Here's that Y we talked about, and Y just equals 1 minus X. Now, at this point, I would really like you to try to solve this yourself, because algebra is all something you have done before, but maybe it's been a while, all right? And if it has been a while, this is just a good way to kind of remind you. When you have 1 minus X times that 70.9 number, you use what's called the distributive property to figure it out. And so what you'll do is you'll first multiply 1 times 70.9. You'll end up with positive 70.9249. But then you're going to go minus X times that. You'll have minus 70.9249X. So this is the joy of the distributive property. If you do all this and you do it correctly, and you have to get the x's on one side and the numbers on the other side, and then divide the x number by both sides to get x by itself, you end up with 0.6012, which is 60.12%. And then because y equals 1 minus x, 1 minus 0.6012 gives you 0.3988 or 39.88%. So see if you can do this by yourself, okay? If you get stuck, call me in. Go see the Learning Success Center, the AVID Center. They can help you out too. But this will be an important skill going forward, that you know how to use this distributive property, solve for x, all that kind of stuff. And by all means, there's no shame if you don't remember, because this isn't something that a lot of people do every day. So reach out to me or the LSC AVID Center. People are here to help you, definitely. Here's another thing with isotopes. Antimony is another element. It has a symbol Sb. There's two main isotopes, all right? And the average atomic mass of antimony, 121.76. And the question is, will you ever have one atom of antimony with 121.760 AMU? And the answer is no. You aren't, because you're going to have 120.9038 antimony 57-ish% of the time, and you're going to have 122.9042 antimony about 42% of the time. But you'll never have an atomic mass, one atom with 121.76. And remember, this is the number that's on the periodic table. And if it's a fake number, you might think, what the heck? All right, why are the chemists including this number on the periodic table? Well, the final answer is that we deal with so many atoms at one time. We're not talking about one atom or 10 atoms or 100 or 1,000 or 1,000,000. We're going to talk about just billions upon billions of atoms. And this average mass number is a great way to talk about all of the atoms of antimony together. But if you had a big bag of antimony and you pulled out one atom, you'd never have an atom of 121.760 AMUs. You'd have one of the other two masses, 57% or 42% of the time. This number is statistical. So in the lower right-hand corner right here, I have a silly graphic, far side, I think, and it shows, have you met our 1.5 children? And in Oregon, there's supposedly 1.7 to 1.8 kids per family. Now, that's an average in the state of Oregon. And you're never going to go to a house and see, 7/10 or 8/10 of a kid. That's gruesome and morbid beyond even my weird science fiction perspective. However, when you think of all the families in the United States, and in Oregon, in this case specifically, that's more reasonable, because sometimes you'll have only one kid, and sometimes you'll have two kids, and sometimes you'll have 0 kids, and sometimes you'll have like 5 kids, right? So the average is important, and that's where these numbers come from. So the 121.760 is an average, all right? You don't have any individual antimonies at that. But when you're dealing with tons and tons of antimony at one time, and we will be, that's where this number becomes really important.